All right, today we're going to dive into a classic problem from Irodov's legendary physics book. It helps us answer a really cool question. If you could actually journey to the center of the Earth, what would gravity really feel like down there? Let's find out.
So let's start with a little thought experiment. Imagine you could drill a tunnel straight through to the core of a planet. As you go down, does the force of gravity just get stronger and stronger until it crushes you? Or does something totally different, something kind of counterintuitive happen? That's the mystery we're going to solve, and the key is a really powerful idea called the shell theorem.
So, let's take a look at the problem itself. Here's the challenge laid out for us right from the textbook.
Okay, so what's our mission? We need to figure out two things. First, the gravitational field, which you can just think of as the force or the acceleration of gravity. And second, the gravitational potential, which is all about energy. And we need to find the equations for these two things anywhere, whether we're outside our perfect little planet or tunneling deep inside it. And once we have that, we're going to draw a couple of graphs to see what it all looks like.
First things first, let's get the easy part out of the way. What does gravity look like when you're outside the sphere, just looking at it from a distance? So this is where we get to use an incredible shortcut, something Isaac Newton figured out called the shell theorem. And the first part of it is super convenient. It basically says that as long as you are outside a nice, uniform sphere, you can pretend its entire mass is squeezed into one tiny single point right at the center. And because of that, the math becomes really simple. We just get to use the standard, everyday equation for gravity that you probably already know. The force depends on the total mass, m, and it drops off with the square of the distance, r, from the center. Easy enough, right?
Okay, that was the warm-up. Now for the main event. What in the world happens when we actually cross the surface and start digging inside the sphere? This is where it gets really interesting.
You see, the shell theorem has a second part, and this one is a bit of a mind-bender. It says that any mass that's farther from the center than you are, that entire shell of material outside of your current position, exerts zero net gravitational force on you. It's like the pull from the stuff above you to your right is perfectly canceled out by the stuff above you to your left. It all just adds up to nothing.
And this right here illustrates the main idea perfectly. When you're outside, the whole planet is pulling on you. But the second you dip inside, the only gravity you feel is from the smaller sphere of mass that's still underneath your feet.
So, that leads to the next logical question, doesn't it? If only the mass below us matters, we need a way to figure out how much mass that actually is. It's not the total mass m anymore, it's some new, smaller mass that's constantly changing as we move. Well, we can figure this out in three pretty simple steps. First, we find the sphere's overall density. That's just its total mass divided by its total volume. And since our problem says it's a uniform sphere, that density is the same everywhere. Second, we find the volume of that smaller sphere that's beneath us at our current radius, r. And finally, we just multiply that smaller volume by the density to get our effective mass, the m inside that's actually pulling on us.
And now for the really crucial part. We take our normal gravity equation, but instead of the big M for total mass, we plug in our new formula for the effective mass, m inside. And after you shuffle the algebra around a little, something amazing happens. The gravitational field inside the sphere is no longer proportional to 1 over r squared. Nope. Instead, it's directly proportional to r, your distance from the center.
And that gives us the answer to our question from the very beginning. If you plug in r equals 0 into our new equation, what do you get? The gravitational field is 0. You wouldn't be crushed at all. You'd be totally weightless, just floating there in the heart of the planet because all that mass would be pulling on you equally from every single direction.
Okay, so we've nailed down the force. Now let's switch gears and look at the energy of the system. A good way to think about this is like a gravity well. The gravitational potential, which we call phi, tells us how much energy you'd need to climb out of that well from any given spot. Now, don't get intimidated by these formulas. They actually come from a pretty standard process. To get the potential, you just have to integrate the gravitational field. So for the outside case on the top line, integrating the 1 over r squared field gives you that familiar 1 over r potential. And for the inside case, integrating the field that was proportional to r gives us this new formula with an r squared in it. It's a perfect example of how the math just ties these concepts together.
Now here's a really common trap, just staring at the math. The real physical idea here is to picture that gravity well. The potential is just a number that tells you how deep you are. And since the potential value is the most negative number at the very center of the sphere, that means it's the absolute bottom. To escape the planet, you'd have to climb all the way out of that well.
Okay, we've done the heavy lifting. We have our equations for both the field and the potential. So now, let's bring it all together and actually create the plots that the problem asked for in the first place. First up, let's take a look at the strength of the gravitational field, G, as a function of our distance from the center, r. The graph of the field strength is really like two different plots stitched together. It starts at 0 right at the center. Then, it goes up in a perfectly straight line, growing stronger and stronger until it hits its maximum value right at the surface, where r equals r. But the instant you step outside the surface, the rules change, and the field starts getting weaker again, falling off with that classic inverse square law.
All right, now let's do the same thing for the gravitational potential, phi. This graph is going to show us the exact shape of that energy well we were just talking about.
What's so cool about this potential graph is how smooth it is. It starts at its lowest possible value, the bottom of the well, right at the center. From there, it curves up, kind of like a parabola, until it gets to the surface at r equals r. After that, the curve keeps rising, but it starts to flatten out, getting closer and closer to 0 the farther away you get. That continuous curve is our gravity well.
So, after all that, what are the big takeaways? If you're going to remember anything, remember these 4 things. 1. Outside a sphere, gravity is simple. It just acts like a point. 2. Inside, things get weird because the mass above you cancels itself out. 3. That leads to the incredible conclusion that gravity is literally 0 at the center. And 4. The force of gravity is actually strongest at the surface, not deep inside.
And I'll leave you with a final thought to chew on. Our whole solution was based on this idea of a uniform sphere, where the density is the same everywhere. But real planets aren't like that. Earth is way denser at its core than at the crust. So how do you think that would change the shape of these graphs? It's a great follow-up question to think about. Thanks for joining me for this little explainer.